Hello everyone. So in the last video we saw this tree on the left that has 1 through 9 and 9 nodes, and when you're trying to find that ninth node it takes n steps to go all the way from 1 to 9 because you say 1 isn't 9 so it must be greater than 1, and you follow that left pointer. 2 is not 9 and it must be greater than 2. Follow that right pointer all the way down to the end of the tree. So this is a very long tree, and you're finding the largest value at the very end, and that takes 9 steps. Now, let's see if we can reduce the number of steps it's going to take to find 9. So I have the second tree over here, and instead of 1, my root is 5. So 5, 6, 7, 8, 9, 4, 3, 2, 1. And this is a much more balanced tree. So even number of children or even height of these subtrees. So if we have 4 as the root of our subtree here, that would be a shorter tree. So we have 2 subtrees here instead of one big one. And getting to 9 is going to take fewer steps. So let's just see how that works. Finding 9. So if I say find here and I find here and I race them down, even though this one started first, this one is finished long before we get there here. All right, so we found 9 here in just 1, 2, 3, 4 steps, whereas here it took 9 steps all the way down. So by balancing the tree, we still have all of the same data here, but by balancing the tree, we got to that 9 much more quickly. So this is what's going to help us improve the time complexity of inserting, deleting, and finding things in our trees, and by balancing those two halves and balancing the subtrees within our tree. We can improve on that yet again. This is again the same data as our original tree, but here we have 6 as the root, and each tree is as full as possible. Right here in our just balanced subtree, we have 4 only has 1 child, 3 only has 1 child. All of these nodes only have 1 child except for the root. Here, the root has 2 children, the 4 has 2 children, the 8 has 2 children, even the 2 has 2 children. Everything has as many children as it can get. And this is because it's a balanced tree. So by balance, I mean each subtree, so the height of this subtree with the 4, 2, 5, 1, 3 is 1, 2, 3. And the height of this subtree is 1, 2. And so when we're using binary search trees that are balanced, we never want the height of the subtree or of the 2 subtrees to be more than 1. We can't help having 1 difference in their heights, but we never want it to be more than 1, and this is going to make it a lot faster. Because again, now if I want to find 9 here, and I want to erase it finding 9 here, I say find here, and I say find here, and it's going to take a lot less time in this more balanced tree than it is in this tree. And that's because it's only taking 1, 2 steps instead of 1, 2, 3, 4 steps to get to 9. Right, so balanced trees are fuller trees, and they take less. The time complexity to find, insert, and delete on a balanced tree is going to be O log n instead of the O of n that it took with this tree here. Right? So we have an O log n time complexity for inserting, deleting, and finding, and that's pretty fast, right? Remember that we have constant time, which is removing the root would be constant time. You just do one action, and it's always the same. But the next fastest thing that we've talked about is logarithmic time, where we can do things in log time. And the reason that we're doing that with this tree is because every time we make a decision, every time I say, all right, I'm looking for 3, and 3 is less than 6, so I'm going to go down this path, I'm cutting off this whole half of the tree. I don't have to ever look at these nodes. I never have to consider these nodes. I never have to compare 3 to any of these nodes. I'm cutting my options in half every time I go down, and that makes for logarithmic time. I do the same thing here. I'm cutting off half of my tree when I make the decision at the 4 which way to go. Right? So that's why we have logarithmic time. Now, if I'm adding nodes to my tree in a random order, and I'm just getting numbers in, how do I ensure that the tree that I build is going to be as compact as possible? So we are going to have some really simple rules for inserting into a balanced binary tree. So first things first, if I just pick a random number, let's say 34, and I insert that, the first node is always going to be the root. Sweet, easy insertion. Notice now that I have a little 1 here, and that 1 is telling me the height of this tree. So 1 is the height of the subtrees going off of here. And then I'm going to add in, I don't know, 23. Insert that. I'm still saying that 23 compared to 34 is less than 34, so it's still going to the left. Nothing's changed there. Again, there's that little 1 there saying I'm at the first level of the tree. And now this has changed to 2. So this is saying the height of the tree coming off of here is 1 for the root and 2 for its child. All right, so let's try adding another number in here. If I add a 14, then the subtree going off to the left is going to be of height 3, and the subtree going to the right is going to be of height 2. So we're going to have 23 and then its child of 14. And the height of the subtree going off to the right is going to be 0 because there's nothing here. So we're going to have to rearrange these nodes so that there is only one height difference between the left subtree and the right subtree. All right, so I compare 14, 23, I add it in, I update my heights, and then I realize that I need to switch it around. So that's what's called a rotation. The 23 came up and the 34 went down. And I did it that way because if I'd put the 14 at the root, then we would have had the exact same problem we had with the 34 at the root. The 14 as the root would have had a height of 2 coming off of it because we would have had 23 and 34, and that would be 2 as compared to the 0 coming off in the left direction. So that would have had the same effect. So when we're balancing trees, we always want the innermost node, or the node that has the most similar value to the root, to be what changes the root. Becomes the root. And we don't want this tree to only be the root tree. We also want the subtrees to be balanced, right? Because otherwise we'd have a situation like this, where this is a very balanced tree, but it's still not as good as this tree. So we still want the subtrees to be balanced, and I'll show you what I mean there. So if I add in 12, this is still balanced because I have 2 and 1. This subtree is fine because I have 1 over here and 0 over there, and that's a difference of 1 height, so I'm fine. But when I add in 11, say, then this tree is going to not be balanced because I have 2 here and 0 here. So I'm going to have to change those, right? And so I had to change this so the root of the subtree became 12 instead of 14, right? So let's try an example where we add yet another small thing here. So if I add 6, now this tree will still be balanced because I'm going to have 2 here and 1 here, and that's a difference of 1. But this larger tree was not because I had 3 and 1, and that's too much. So I had to bring the whole thing up, and I brought it up with 12. Right? That was the closest thing to the root already. All right, so these rotations get tricky. I'm going to make another video that's all about the rotations here, but first I want you to try it out, try in the worksheet thinking through what the rotations might be, and then in the next video I'm going to go through every possible rotation and show you what we want to do with it. All right, and I'll see you in the next video.